we have to consider an LTI system with the impulse response h of n and the input x of n as illustrated in figure 2.3a. This is figure 2.3a, and over here in the first figure, part A, you're given the impulse sequence and the input sequence to an LTI system. So what it means is that for the given discrete time LTI system, if you apply a digital or discrete impulse delta of n, the output h of n is as given. Okay, the output sequence h of n is this one, right? So what happens now if you apply? So you know what h of n is. Okay, h of n is the response of the system of the LTI discrete time system to the unit impulse delta n. Now what happens when you apply x of n? Okay, so what is the output? You see, the first thing you want to do is to evaluate x of n, as we have talked previously, is to see how we can decompose x of n into discrete impulses delta of n. Now here x of n has two samples, therefore x of n can be written as there is a sample at n equal to 0, so the weight of the impulse becomes 0.5, which is x of 0, and then comes delta of n with it. Okay, plus we have another sample which is at n equal to 1, and the weight will be x of 1, which is twice delta of n minus 1, right? So this is your x of n. So now if we have this decomposition, then it's easy to see what the output, the final output y of n will be. This is done graphically over here in this figure for this is shown in part B and C. So what happens is that if I say that I apply another input of 0.5 delta n, and I know that the system is linear. That means if I scale the input by a weighting, let's say 0.5, then my output, which is h of n, will be scaled by the same amount. So this will be 0.5 h of n, right? 0.5 h of n means that all the samples are halved. Okay, so this is 0.5 h of n. Then another input. Let's apply another input, which is twice delta n minus 1. Now the system, since the system is both linear and it's time invariant, that means if the input is delayed, so if the input is delayed by a certain number of samples, my output will also be delayed by the same number of samples. So my output was h of n, okay, in response to delta n. Therefore my output will also be delayed by the same number of samples, and it will be scaled by the same amount. Okay, so this is due to linearity, both linearity and time invariance. I have an output twice h of n minus 1. Now if I apply input x of n, which is equal to, so I have x of n can be decomposed into two inputs, x1 and x2. Okay, so let's call the first input x1 as 0.5 delta n. Okay, so I'm linearly combining the two inputs x1 and x2 over here, right? So now my input x of n is 0.5 delta n plus twice delta n minus 1. Now due to the principle of superposition, the response due to these two inputs will be the individual responses superimposed. Okay, that means the individual responses to 0.5 delta n was 0.5 h of n, and the response to delta n minus 1 was hn minus 1. So this all adds up. Okay, these two terms, they add up. So plus 2 h of n minus 1. So the response, total response, is the superposition or the the summation of the individual responses. The individual responses were y1 and y2. So this is the response to x1. Similarly, you have the response to x2, which is y2. So yn is y1 plus y2. So it's the sum of the individual responses, 0.5 h of n plus 2 h of n minus 1. This is 2 h of n minus 1. If you if you add them, this is the final result. So this is y of n. right? This is y of n. So these are this is the idea behind the convolution sum. So you see what happens over here is, if you recall in the previous lecture, we formulated the convolution sum in terms of the impulse response and the input sequence. So for any arbitrary sequence which can be decomposed into impulses, the response is supposed to be in terms of the impulse response of the system, which is h of n. So basically, a convolution sum is given as convolution of the input sequence and the impulse response of the system. So if you use this instead of graphical approach, you use the mathematical formulation of the convolution sum. Note that the first thing you note is that since x consists of two non-zero samples over here, 0 and 1, otherwise it's 0. So you have to modify the limits, okay, because we don't have x of minus 1 or x of 2. So k is going to vary from 0 to plus 1. Now if you expand this, there are two terms, x0, then h of n, okay, because these two are functions of k, summation is over k. So this is x0 h of n, then plus x1, where k is 1, hn minus 1, okay, and this is the same thing. The expression for y of n is what you see at the graphical output y of n. Okay, so y of n is basically the summation of these two uh, outputs, 0.5 h of n to hn minus 1, where h of n is depicted like this. Okay, so you add them and you get y of n. Okay, so now the two sequences, 0.5 hn and 2 hn minus 1, are the two echoes of the impulse response needed for the superposition involved in generating y of n. So these echoes are displayed in figure 2.3b. By summing these two echoes for each value of n, we obtain y of n, which is shown in 2.3c. So finally, 2.3c, you have this y of n, which is the response of the two echoes that we have seen. So this is, let's call this y1, y2. So y of n is your y1 plus y2, which are the echoes of your original input sequence, original impulse response h of n. Okay, this is in terms of h of n.